Hi again, everyone. Today we're going to continue our exploration of functions of several variables. And in particular, we're going to look at the idea of a derivative for a function of two variables. And we call these kinds of derivatives partial derivatives, and the idea is known as partial differentiation. Okay, so we're going to look at how we define partial derivatives, how to compute them, and their geometric interpretation. Okay, so we know, let's motivate the subject, we know that from elementary calculus, the idea of a derivative for, say, a function of one variable is very useful in tackling applied problems and modelling. Okay, and the idea of this video is to extend the idea of a derivative to functions of two variables. Okay, so the basic idea is to determine the rate of change in f with respect to one variable while the other variable stays fixed. Okay, so let's look at a simple problem for modelling. The amount of power P available to a wind turbine can be summarised by this equation here. Now we've got a couple of constants and we've got a couple of variables, D and V. Here D is the diameter of the turbine blades exposed to the wind and V is the wind speed. Okay, now a natural question with this problem is, what is the rate of change in the power P if we vary the diameter of the blades, but the wind speed stays fixed? Okay. All right, so let's talk about what a partial derivative actually is. Well, here's a limit definition. You can see the partial derivative of a function of two variables with respect to x at some given point is denoted by this df dx, where the d's are curly, and it's given by the limit of this quotient. Okay, now let's take a little bit more of a closer look at this limit. Notice here that the first variable, or the x variable, is the only thing that changes here. Okay, the second variable doesn't change. All right? And essentially it's the limit of this difference quotient where there's a change in the first variable, the x variable. All right? Now, we use curly d's, df dx, to set partial derivatives apart from the derivative that you learned at school with the straight d's, df dx. Okay? And this notation is also used, but essentially df dx is just the derivative of f with respect to x, keeping the y variable fixed. Now there's a number of different notations for partial derivatives. Some people prefer to use the subscript, so f sub x means df dx with curly d's. And then f sub x evaluated at a point is just the derivative, partial derivative of f with respect to x at a given point, x0, y0. Okay, so let's continue talking a little bit about what this partial derivative means. At school, when you take elementary calculus, you interpret the derivative as the slope of a tangent line. So is there something similar in this partial derivative setting? And the answer is yes. You can see here this grey region is your surface, okay? And at this point x0, y0, we construct a vertical plane that is parallel to the xz plane, okay? Now, so you can think of this green type of plane as a section. Okay, now this section intersects this grey surface to form this blue curve. Okay? And what this partial derivative means is it is geometrically is that it is a measure of the slope of this red tangent line to this curve. Okay, so yes, it is very similar to what you learnt at school. However, in the sense that it is the slope of a tangent line, but the tangent line lies in a special plane. That's the difference. Okay? All right, now with functions of two variables, we have two partial derivatives, df dx and df dy. So the definition for df dy is similar. Here you can see the second, or the y variable, changes here, but not the first one, or the x variable. Again, it's the limit of this quotient. All right? And essentially, df dy is just the derivative of f with respect to y while keeping the other variable, the x variable, fixed. And you can have this subscript notation just like you can for f sub x and f sub x. Okay? All right, so df dy, of course, is just the slope of another tangent line. But here you see the plane, the green plane, in which that's parallel, in this case, to the zy plane. Okay, so that's the biggest difference between this derivative and the previous derivative. Yes, it's still the slope of a tangent line, but the tangent line to the surface lies in a plane that is parallel to the yz plane. Okay? All right, so I guess the important thing, the basic important idea here is to learn how to compute these partial derivatives. So let's see how we actually compute them. We have an idea of what they are, but let's compute them. So here's an example. If this is our function of two variables, then find these two partial derivatives. Okay, so to compute df dx, we hold y as a constant and differentiate with respect to x. Okay, so essentially we imagine all the y's here are just constants and differentiate normally with respect to x. So this is what we want to compute. We want to compute the partial derivative of this with respect to x. Now, if y is a constant, then I can bring this first term, I can bring that out the front to get something like this. And this derivative of y cubed, well, y is just a constant, so y cubed is going to be a constant. If we differentiate that with respect to x, well, this is going to be 0, and this is going to be 2xy. Okay, so we've formed our partial derivative. Notice that it's just, again, a function of, in this case, two variables. Okay, so let's go on and calculate df dy. So in this case, we hold x as a constant and differentiate with respect to y. Right? So df dy is going to be the following. All right, so now let's have a look at what we're differentiating. We're imagining x is a constant and differentiating normally with respect to y. So that first term, the one y is going to go to 1 and the x squared is just going to stay there. And the second term is going to go to 3y squared. Okay, so there are our two partial derivatives. In each case, we just differentiated, well, we held one of the variables fixed and differentiated normally with respect to the other variable. Okay. If this is our function of two variables, then calculate these two partial derivatives and these partial derivatives at the particular point. Now you can see here I've used the subscript notation over here, and I've used the curly D notation over there. You need to be comfortable with both of them. All right? So we imagine y is a constant and differentiate normally with respect to x. So that first term is going to go to cos x, and the second term is going to become y squared. Now, to differentiate with respect to y, we hold all the x's constant, and then just differentiate with respect to y. So, d dx of sine x is going to go to 0, because if x is a constant, sine x is also a constant. And d dy of xy squared, that's going to become 2xy. All right, so let's calculate the value of these derivatives at these given points. So we go up to our partial derivative and substitute in x equals 0 and y equals pi. And we're going to get cos of 0 plus pi squared, which is just 1 plus pi squared. And now we go up to here and substitute in x equals pi, y equals 0. That's going to give us 0. Okay, so notice up here we've got functions for our general derivatives, and then at certain points we get just numbers for our answer. Okay, now notice that we haven't actually used the definition of what a partial derivative is. We haven't used the limit definition yet. Okay, but the following independent learning exercise is an interesting case. Okay, here's a given function. We want to show that the derivative, partial derivative with respect to x, is 0 at the origin. Now, if you hold one of these, or if we hold y fixed and differentiate with respect to x, then actually we get something that's undefined because we're dividing by 0. So how do we work this out? Well, a hint is to use the limit definition of the partial derivative of f with respect to x at the origin. See if you can do it. Now, what rules do we know from basic calculus? Well, we know the product rule, the quotient rule, and the chain rule. Are there similar analogues for these partial derivatives? And the answer is yes. So if we have two functions, u and v, both are functions of two variables, then we have the following product rules, remember, where the subscripts are partial derivatives. And we also have quotient rules. Okay, so it's not a massive leap from the basic calculus that you know, the product rules, quotient rules, to these partial derivatives. Okay, and of course these things are designed to help you in your calculations of partial derivatives. Okay, so here's an interesting example. Suppose we've got a surface that is a paraboloid. Okay, now let's think about the plane x equals 1 that intersects that paraboloid. So here's a little picture of what's going on. The yellow surface is the paraboloid, and then you've got this blue plane, the plane x equals 1, and there's an intersection that is a paraboloid. Now, the question asks you to calculate the slope of the tangent line to the parabola at the point 1, 2, 5. Okay, so the slope of this tangent line is drawn in. We want to calculate the slope of that tangent line. And a good question is, well, yes, we want to calculate some sort of partial derivative, but do we want to calculate df dx at this point or df dy? Okay, and you can see along this plane, in this plane here, x is fixed at 1, but y can vary. So that tells us that we really want to calculate df dy at the point. Okay? So we wish to calculate all right, so going back to our picture, this is the point 1, 2, and we want to calculate df dy at the point x equals 1, y equals 2. Okay, so let's calculate the partial derivative and then sub in x equals 1, y equals 2. Okay, so remember, we think of x as a constant and differentiate normally with respect to y. So that's going to be 0, and this is going to be 2y. Now I've kind of been we're not actually using a definition here, so this is not. I'm going to change that to we have. All right. Now all we need to do is substitute. Substitute in x equals 1, y equals 2. Now there's no x's here, so it's just 2 times 2, which equals 4. So, what is the slope of this tangent line? Well, it's going to be positive 4. Okay. Now that was a particularly good example I found because it forces you to not only do the computation, the partial derivative computation, but it forces you to think geometrically about what's really required here. Okay, we can also talk about second-order derivatives. Okay, the calculus that you learnt at school, you would calculate second derivatives and do things with them. So, you know, things like calculating maximums and minimums of functions and things like that. Yes, there is analogues for these partial derivatives. Okay, and you can see here, for so-called second-order partial derivatives, we have either two subscripts or these squareds going on. Now, this sort of notation, the notation for second-order partial derivatives it changes. It's not universally just one thing. Okay, so you can see here. By this we mean, okay, we take df dx, and then we take the partial derivative of that again. Okay, so that's basically, it's just a derivative of a derivative. Now, one thing that's important to point out, there are 4 second-order partial derivatives, and the two in the middle are known as mixed partials, because you can see you've got x's and y's here and here. All right? Now, a reasonable question is, does it matter which way I differentiate? If I sort of switch the x's and y's around here, does it really matter? If I see here, I've differentiated with respect to x first and then y. Here it's first with y, then x. Okay, now the order in general is important. Okay, but there are, we're going to see a very important exception in a little while. But let's calculate some second order derivatives and see how we go. All right, so to calculate the second order derivatives, the first thing we do is calculate the first order. Okay, so f sub x is going to be, remember, y is a constant, differentiate normally with respect to x. For df dy, or f sub y, imagine x is a constant and differentiate normally with respect to y. So this is going to become x cubed. So let's calculate our second order partials. So to get f sub xx, we go up here, differentiate with respect to x while keeping y as a constant. So this is going to become 6xy. To calculate f sub x sub y, by that we mean the following. So we go up to f sub x and calculate the partial derivative with respect to y. So this is going to become 3x squared. F sub y sub x, and by that I mean this. So we go up here, and we differentiate with respect to x. And finally, f sub y, go up to here, differentiate partially with respect to y. So that's going to give us 0. Okay, so we've quickly calculated the 4 second-order partial derivatives, and we're asked to notice something about the mixed partials. Well, there's one mixed partial, and here's the other one. We see that the mixed partials are equal. Now, in general, that's not true. Okay? And the following theorem gives us sufficient conditions under which we do have this equality. Okay? So if f and its partial derivatives are defined throughout an open region containing a point, and all of these functions and its derivatives are continuous at the point, then the mixed partials are equal at that point. Now, what's the importance of this theorem? Well, it can save us time in computing the mixed partials. So this is just this is going to have all the continuity properties that you need to apply the theorem that I just showed you. So really, all I need to do is calculate 3 partial derivatives. I don't really need this one here because I know that if I switch the x and the y here, I'm also going to get 3x squared. So it's a good time saver. That's one of the reasons why it's useful. Okay. All right. So a little bit more on partial derivatives. Now, for functions of 2 variables, partial derivatives are a little bit stranger than what you've seen at school and the derivatives there. Here's an example of a function that has a discontinuity, say, at the origin, but the partial derivatives exist at the origin. Okay, so that's a bit strange. How would you explain that? How do you explain that? Okay, and I've left that as an independent learning exercise. And another good exercise is to try to construct a function whose mixed partial derivatives do not commute. In other words, the mixed partial derivatives are not equal. Okay, try to find such a function. All right. One more example. Consider the function given by this f here. Calculate these 2 second-order partials, and then use part A to show that this equation is satisfied. All right. So let's do part A. We have the following. So df dx is going to be 2y, and df dy is going to be 2x. So I've just calculated the first partial derivatives. So let's go and calculate the second. So again, you can see I'm using the curly D notation here. So if I go up to here and take the partial derivative with respect to x, well, y is constant, so this is just going to be 0. And similarly, if I go up to here and calculate, this is what I want to calculate d squared f dy, then here x is constant, so this is just going to go to 0. So the value of these 2 second-order partials are both 0. All right, so let's show that this equation holds. So the left-hand side of 1, it's d squared f dx squared plus d squared f dy squared. And then from A, we know that this is 0 and this is 0. And so we get 0, which of course is the right-hand side of 1. Okay, so we've shown that the left-hand side and the right-hand side are equal. Therefore, what does it mean? This function must satisfy this equation. All right, now this equation here is known as a partial differential equation. Okay, now in particular it's known as Laplace's equation. Okay, so we call it a partial differential equation, or a PDE, because it's an equation and it has partial derivatives inside it. And what part B tells us is that this particular function f is a solution to this PDE, this partial differential equation. Now, the particular partial differential equation that I showed you is known as Laplace's equation. And it's very important in the modelling of heat conduction, fluid flow, and electromagnetics. And usually what we do when we see a partial differential equation is that we want to solve it somehow. Okay? So that's a little bit of an introduction into the partial derivatives, and I'll talk a little bit more about what we can do with partial derivatives in the next video.